Angelo Casciani with the talk Neuro-Symbolic Conversational AI for Reliable Production Service Intelligence. Yeah, you can use it.
Okay, so thank you for the introduction, and good afternoon everyone. I'm Angelo Casciani from Sapienza University of Rome, and today I will present you the work that we did with my supervisor regarding Neuro-Symbolic Conversational AI systems for reliable process intelligence. Now, the advent of Industry 4.0 together with the wide adoption of IoT devices has shifted the classical manufacturing industry into cyber-physical production systems that are continuously monitored by these devices, and organization wants obviously to leverage this kind of data and this continuous stream of data to both improve their decision making, also amplify human expertise, let's say. Just a quick clarification about the notation that we will use. In particular, when I talk about production system, I mean the entire set of software, hardware, machines, and human resources and business rules that made up a system that is actually used to carry out several production processes. That are the ones that turn the raw materials into finished goods. And in doing so, as we said, these production processes are actually monitored, and there are many data that are produced to actually, let's say, back these kind of digital models that are used to amplify human expertise. And in this picture, we talk about production service intelligence, that is indeed the representation, the so-called digital twin of operational, organizational operation. And this is used to actually also foster the collaboration with the human user. And these two services for production intelligence are actually used in a, let's say, cloud-native way and are contacted by standard APIs. And in particular, we can consider in this presentation techniques like simulation, model checking, and process mining, that they all have different let's say focuses, in particular predictive or compliance checks for model checking, or descriptive analytics for process mining. Now, what is the problem here? The problem is that at the moment in an organization, when you trying to use this kind of tools, there is usually an expert that is using a specific tool. And this tool usually have a needed expertise to be used, and several tools present fragmented interfaces and require each. Sorry?
Absolutely not. Can you?
Okay.
No, it's absolutely. If you put it a bit far away. Yeah.
Okay. Okay. Like this? Okay. Okay. So basically, what I was saying is that they are used in silos. As they are fragmented in several interfaces that needs to be contacted by the actual expert in this tool. And in particular, to solve multi-perspective analysis like the one reported here in this use case require manual integration. What does it mean this? Let's, for example, consider this scenario. We have new order that arrives, and the production manager wants to actually foresee whether the deadline for this order can actually be met. To do so, it needs to contact first the expert in process mining to analyze historical traces. Then it needs to contact expert B for running simulations and carry out a what-if analysis of the new production plan. And finally, verifying that the constraints regarding the safety of the production process are met, so the process is still compliant with the rules. Now, to do so, obviously, this is a dull task, and the poor plant operator needs to go on Excel and directly merge the various data and come up with a new production plan. Now, the immediate thing that comes to mind at the moment is, okay, why don't you use just LLMs and you're fine? Well, we are not fine with it, unfortunately, because there is a lot of empirical research in AI in general, but also in automated planning in particular, that showed that these models do not actually come up with a proper reasoning process to produce the results, but they act as approximate plan retrievers. What does it mean? That if they were exposed to particular problems in their training dataset, they were able to find a similar solution. But this is not proper reasoning in the real sense, in the, let's say, rule-based reasoning of traditional AI. Moreover, what we need to actually point out is that they are very affected by small paraphrases of the questions, and this is showed by a recent ICAI paper, and also large reasoning models that are the ones that are based on chain of thought technique are actually not safe because they can produce results, but with reasoning traces that are flawed actually. And they also lack self-verification mechanism that can be defined as sound in the proper AI technique. And this is obviously unacceptable in production system, as you cannot imagine an hallucinated safety constraint, for example. Now, that is why before I will present you our solution, we made the analogy with the pretty famous at the moment Thinking Fast and Slow book by Daniel Kahneman. In this book, he basically characterized the human perception, human mind, in two kinds of systems. System one that is fast, intuitive, and data-driven. You can imagine, for example, your ability to recognize a face. This is system one. And on the other hand, we have system two that is more deliberative, more slow in its processing, but also analytical, and you can actually trust its conclusion. For example, if I put you a multiplication in front of you, you will need some time to process it and produce the result. This is system two. And we can actually make the analogy with generative AI for system one, because it does not produce the results with effort that is actually comparable to the complexity of the problem, because it produces tokens at a constant rate. And system two, that is symbolic AI, which is rule-based, so it's sound in the results it gives you, but at the same time it needs, for example, a human that craft the rules for the system. Now, that is why in this shift we actually adopted a well-known paradigm in automated planning, that is LLM as a formalizer. But before talking about that, just to be on the same page, automated planning is a well-known area of traditional symbolic AI, in which you basically declaratively specify your domain of interest, and you want to achieve a certain goal, and you specify the goal declaratively, and then there is a component that is called the planner that will actually come up with a solution that is not a script in Java, but is a plan that is computed on the fly based on the domain and on the given goal. Now, in this area, researchers came up with two possible applications of LLMs. The first one, directly to use them as planners, so to come up with the results directly, which is obviously not feasible at the moment because you cannot trust their stochastic results. But at the same time, you can use them, as also Anne was saying this morning, you can use them to actually perform what they do better, that is handling natural language, basically. And in particular, in this case, our natural language is code in PDDL, Planning Domain Definition Language, that is the de facto standard language for defining these domains and problems. Now, with keeping this in mind, we can actually finally come up with our solution. And we envision this kind of neuro-symbolic integration. In this slide, you can see the general philosophy. So we are not characterizing what kind of services we are using behind to back our solution. But what you need to imagine is that we have the user here that will actually go to the conversational system to ask its question in natural language, because you need to think that it can be an expert or even a non-expert user that needs to contact several services with which some of them may be familiar and some of them not. So the natural language question comes to a router component that is the one that, as the name said, perform the routing of the question, that if it's a question that regards a single service, it can directly route it to the service before there is a little hop, but we will take it later. Otherwise, if the question is like the one before, a scenario that requires the interaction with multiple tools at once, we need to contact an orchestrator that for us will be the actual planner that we talked about before. And that will come up with a proper sequence of invocation that is actually sound. We have mathematical guarantees that this sequence of invocation is sound, it's not made up by the LLM. Then we will contact the proper services, but before contacting them, we need to actually translate the natural language intent of the user into something that is machine readable for these services that are contacted behind. And in particular, we will need API translators for these various services that are behind. Each of these services will rely in the last layer on its own data that can be or directly the event log recording the execution of the production process, so directly on the raw execution data, or there can be several models or representation that are used by the specific service. We will later see an instantiation to better understand this. Indeed, in our instantiation, we will consider the three production service intelligence microservices that we introduced before, that are simulation. Simulation is a well-known technique in production engineering in general to come up with what-if analysis and let's say scenarios of production. In our case, we will consider discrete event simulation as a service that will take in input the digital twin of the process, so in this case our representation of the event data, and a scenario of simulation. For example, I want to fulfill this order of 100 pieces within a certain deadline. And to do so, we have implemented it with the well-known library SymPy. And the simulation will produce, obviously, the KPIs, so the key performance indicator we are interested in. They can be, for example, the throughput of the process, the processing times of each station that compose the production line, and so on. Now, then we have model checking. Now, as you can imagine, we are not fine only with probabilistic estimations given by the simulation, but we will need safety guarantees, compliant guarantees on the fact that this cyber-physical system is actually compliant with its specification. Sorry for the repetition. In this case, we adopted the formalism used by our model checking engine, which is Supal. In particular, it relies over a probabilistic time automaton of the production process, and we will unfortunately use timed computational tree logic to do so. And we will produce Boolean results in output. Last but not least, we also foreseen a process mining service. Process mining can be used to work directly over the event log of the production. So in this case, we do not use a particular specification. Why? Because it supports several tasks that can be, for example, to produce its own model of the production that is underlying the event log through the process discovery, for example. In our case, we use an inductive miner to come up with the pattern of the production process. Then we have conformance checking, in which we can actually see whether the process that we observe in the event log is actually able to be in accordance with the procedural representation, and so on. So this is the instantiation we have said. And obviously we can use the planner to come up with the invocation, so I need to speed up a little bit because I want to show you the results of the evaluation, but we already discussed about this. So we actually perform a preliminary evaluation over a real physical twin of an automated company. In particular, this is made up of Lego Mindstorm station that are processing pieces that comes in and comes out of the production line. In particular, our preliminary evaluation was composed by a dataset of 1.5K natural language request and expected answer pairs, and we asked whether our framework was able to handle both the routing and the encoding of each request. These are the results. So as you can imagine, proprietary models as GPT 5.1 are able to perform all the tasks in a pretty nice way. But what comes to our eyes is that also models that are pretty small but are open weights can actually be implemented and employed in the framework. And this is obviously very nice because in this organization we have several privacy concerns, because we do not want to send our production data to these API services and big American company. That is why we can implement also the framework with the open weights model, but not with the smaller ones that tend to directly hallucinate the results. So talking about stress validity very quickly, we actually try to mitigate the stochasticity of the LLM, trying to repeat and average the results 5 times for each test that we run. We did not use any kind of fine-tuning for this, but just prompt engineering. And we try to make reproducibility as much as available as we can, Dockerizing everything. And the problem is that obviously the utility of the tool depends on also the services that are using the PSI tool, but also on the data that we are using, unfortunately. But we can actually say that the logical consistency of the data is guaranteed because the results are not hallucinated by the LLM. So this is basically all from me. So if you have questions, feel free to come by tomorrow at the poster session. Thank you.
We have time, a couple of minutes for questions.
Okay.
Any questions?
We do the poster session. We have a poster session.
Okay.
So the rule is everything is
Perfect.
Okay, I was prepared.
perfect.